Bună ziua și vreau să încep prin a mulțumi organizatorilor pentru invitația făcută de a participa la Simpoziul Național de Chimie din Craiova, octombrie 28, 2022. Numele meu este Liliana Lefticaru și sunt profesor de geochimie la Southern Illinois University, Carbondale, Illinois, United States. Câteva lucruri despre mine. Am început ca geolog, am terminat facultatea de geologie la Universitatea din București, în România, după care m-am mutat în Statele Unite, unde am obținut un master la Northern Illinois University. La aceeași universitate am obținut și doctoratul, studiind problemele geochimice. După care am fost angajată într-un program coordinat de NASA, un program de astrobiology la Indiana University, Bloomington, în Indiana. Cum am menționat înainte, sunt profesor la Southern Illinois University și ca geochimist mă uit sau cercetez în special problemele chimice care au relevanță la problemele de mediu sau problemele de energie. Prezentarea mea din astăzi va fi făcută în engleză. Sper ca lucrul acesta să nu afecteze prea mult înțelegerea dumneavoastră a problemelor pe care le voi prezenta și vă rog foarte mult, dacă aveți întrebări, să mă contactați prin e-mail sau telefon sau alte social media. Încă o dată vă mulțumesc pentru invitație și sper ca prezentarea mea să fie interesantă. Let's start, yes? As I mentioned in my introduction, the main area of interest for my research pertain to solving environmental problems. And as you know, there are many environmental problems nowadays that we need to address and find solutions. However, there are very few solutions that actually work. And the question is, why is that? Well, because most of the processes in natural systems occur at the nanoscale, and solving these problems involve us looking at processes that occur at this scale. Of course, nanoscale processes involve nanoparticles. What are these nanoparticles? Nanoparticles have sizes between 100 and 1 nanometers, and they display size-dependent property compared to the bulk phases. The property of materials actually change as their size approaches the nanoscale, and the percentage of atoms at the surface of the material become significant. Couple of examples, there are nanoparticles around us, in air, in water. We breathe them, we ingest them. Viruses, most of the viruses are also have nanoscale dimensions, and you know how powerful these viruses can be in affecting, for example, the human health. One question that is out there is, why are these nanoparticles so important? Because they are really, really tiny. Does the size matter? Well, let's look at an example. If we have 1 centimeter cube, the total surface area is 6 square centimeters. If the same cube is divided in 1 millimeter cubes, then the total surface area is 60 square centimeters. If we divide the same cube in 1 nanometer cubes, then the total surface area is 60 million square centimeters. So indeed, the smaller the particles for the same volume, the higher the reactive surface area they have. So this provides a tremendous driving force for chemical reactivity, diffusion, and other physical and chemical properties. So this is why we have to look again at the nanoscale to understand processes that occur in the environment. One important aspect when we study different processes in the environment is that we need to have a very clear understanding of how this material behave. So for a very long time in school, we have been taught that doesn't matter how large a crystal of, let's say, quartz or calcite is, that crystal is going to have exactly the same property of quartz or calcite, so the size doesn't matter. However, in 2008, Alexander Navrovsky and some co-authors published a very important paper in Science in which they show that the thermodynamic properties of a group of mineral iron oxides depends on their size. So in this graph that you have on the left, you can see that the enthalpies of water vapor adsorption for different iron oxides varies with their size. This was a very important aspect because, for example, iron oxides are found on Earth in acid mine drainage environments. We know they exist on Mars. They have that red color specific to the ferric iron, and they are very important in many processes. So this result was very important because it tells us that the same mineral, for example, goethite, will have different properties depending on the size of the crystal. This result was very important because for many researchers, they had to change their way of looking at the natural processes and coming with understanding of what happens again at the nanoscale. Another question that is out there: can we actually follow this type of processes at this small scale? And the answer is yes, as the new technologies have been developed over the years. We are able nowadays to actually study these processes at the nanoscale. If we want to investigate crystals, for example, if we want to investigate quartz crystals, which usually occur in large sizes, we can use, for example, microscopes in visible light. However, if we want to look at nanoparticles, we need to find wavelengths of similar or smaller magnitude to the size of the object under investigation. Specifically, to investigate atomic molecular structures and nanoparticles, we can use X-ray, electrons, and neutrons, since they can have wavelengths about the size of the atom. So we have to go very small. Radiation wavelength can vary over many orders of magnitudes. So for example, we have a radiation with a wavelength of 1000 meters, characteristic to radio waves, or sometimes the dimension can be very small, like 10 to the minus 15, which is characteristic to gamma rays. Because we are interested in studying nanoparticles, atoms, and molecules, we have to look at X-rays to employ them to interrogate the matter. What are X-rays? They are electromagnetic waves similar to visible light, but situated at the high energy short wavelength end of the electromagnetic spectrum between the UV light and the gamma rays. Their wavelength, around 10 to the minus 9 meters, is comparable to the interatomic distances, which make X-ray very important if we want to study small atoms, molecules, and also interrogate bonds. Where can we find this type of X-ray machines? Well, we have them in our laboratory. If we want to study, for example, crystals, we have we employ X-ray diffraction. We have them in the hospital, and we also can find them at synchrotron facilities around the globe. The difference between synchrotron light and X-rays used in hospital is their brilliance. A synchrotron source is 10,000 billion times brighter than a hospital X-ray source. So if we really are interested in getting the more a lot of information from our samples, we need to go and use the facilities present at the synchrotron facility. So what is a synchrotron and how it operates? A synchrotron is a particular type of cycling particle accelerator in which we have a central source of electrons, and these emitted electrons are accelerated to extremely high energy, and the resulting beam travels around a fixed closed loop path, meaning in a circle. The magnetic field, which bends the particle beam into its closed path, increases with time during the accelerating process. There is only one single physical phenomenon which is used for by synchrotron facilities, and this principle says that when a moving electron changes direction, it emits energy. When the electron is moving fast enough, the emitted energy is at the X-ray wavelength. The resulting X-rays are emitted as dozen or thin beams, and these beams are directed at different axes, which are the beam line next to the accelerator. This type of machine operates day and night with short periods of shutdown for maintenance. The synchrotron produces X-rays, which are usually called hard X-rays. These X-rays are the highest energy X-rays. They have a wavelength between 10 to the minus 1 to 10 to the minus 2 nanometers, and the energy is in the range between 10 and 120 keV. Usually in the synchrotron science, we usually talk about the energy rather than wavelength. Because of their higher energy, this type of hard X-rays penetrate deeper into the matter than soft X-rays, and these soft X-rays have usually energy below 10 keV. The synchrotron X-ray beam can have other important properties, including a time structure so that it can flashes, coherence, making it a parallel beam, and polarization. So in addition to being absorbed by a material, X-ray also can interact with the atoms, giving rise to diffraction or scattering of the X-rays. X-rays absorption can also be followed by re-emission of the energy absorbed, for example, as fluorescence. This interaction with matter are used to gain information about the composition of a sample, including the type and location of individual atoms within it. There are many techniques which are employed at the synchrotron facility, but some of the most common techniques include X-ray diffraction, X-ray scattering, X-ray absorption spectroscopy, photoelectron spectroscopy, infrared spectroscopy, X-ray microprobe, protein crystallography, and many others. For the remaining of my talk, I'm going to give an example of a research problem in which I employ the synchrotron techniques to answer a very important question, and this is what happens with arsenic in acid mine drainage settings. So acid mine drainage is a large environmental problem in every single country because everybody is mining and has been mining different resources for a long period of time. There are many abandoned mine lands all over, and at these places there is a lot of mining waste left without remediation. This mining waste is usually weathering, and during weathering, acid mine drainage is produced. This acid mine drainage is very toxic, contain very high concentration of toxic elements. Sometimes sediments are associated with these acid mine drainages. So the question that I was trying to answer is that is there any attenuation of the arsenic within the sediments associated to acid mine drainage? So why should we care about arsenic? Arsenic is a potential carcinogen, meaning that it can produce cancer, and the most common metalloid contaminant in drinking water sources globally, affecting the health of millions of people through natural and anthropogenic contamination of drinking water sources. Because of its environmental abundance, toxicity, and potential for human exposure, arsenic has been designed the #1 priority toxin by the Agency for Toxic Substances and Disease Registry. In the United States, the Environmental Protection Agency, EPA, has adopted a maximum contamination level of 10 micrograms per liter in drinking water. However, in watersheds affected by mining, arsenic is of course present in much higher concentration and is one of the most prevalent toxic and carcinogenic metalloid and a common contaminant of soil, sediments, and groundwaters. It is very important for us to understand what type of complexes arsenic can make in solution, and also how these complexes interact with a certain surface. So for example, if we look at the pH-EH diagram on the left side of the screen, you can see that in at low pHs, pH between 0 and let's say 4 or 5, arsenic can occur in oxidized environments either as a neutral species or a negative charged species. Why is this important? Well, it's very important because negatively charged species can be absorbed by a surface which has a positive charge, while a species which doesn't have any charges cannot be absorbed by any type of surfaces. So this type of species usually can travel and spread over all large areas without being attenuated. Now, what type of interaction this type of aqueous species can have with the surface? So again, they can be adsorbed as outer sphere complexes. These are complexes which are weakly adsorbed by the surface. They can be released very easily in solution. They can be adsorbed as inner sphere complexes, which are stronger, have stronger bonds. They can be incorporated within the solid as incorporated and sequestrated within the solids, or they co-precipitate with other contaminants on the surface of these solids. So there are a variety of mechanisms by which arsenic can be attenuated by the solids. The question is which one actually occurs in the site that I'm going to talk next. The site where my research occurred is called the Top Simcoe site. This site was an abandoned coal mine, which is located actually very close to my university. The site consists of about 30 acres of underground mining works and surface mining operations that were actively mined between 1890s and 1975. In 1975, the site was abandoned, no remediation occurred. However, a remediation system which consisted of bioreactor and wetland system was built in 2007. So what you see here is a view of the remediation system. The bioreactor was built very easily, so there was a hole which was dug, is shown in here. At the bottom of the hole, there was installed a couple of pipes and also limestone. On top of this layer, there was a organic matter layer, consisted of leaves and wood and other materials mixed up with limestone. And the idea was that the iocimine drainage, which will be collected over the whole site, will accumulate on top of this organic matter. And as it infiltrates through the organic matter, biological processes will occur, including iron reduction and sulfate reduction. And iron and sulfur will recombine to form, for example, sulfides. The treated water then was collected at the bottom of the bioreactor and then pushed through a agri drain, and then will be pushed towards the wetland. So in this picture, you can see here, this is the bioreactor lake. The water will infiltrate all the way to the bottom. The agri-drain is here. The water is coming out, the treated water is coming out here. And then you have this type of wetland, which was put in place to enhance remediation of the acid mine drainage, in addition to remediation happening in the bioreactor. On the left here, you have a view of the site, and you can see here, this is the bioreactor, and then the wetlands, this S-shaped channels, and theoretically the treated water will reach the local Sycamore Creek. However, this type of remediation worked for a very short time period, after which the affluent coming from the treatment had actually lower pH and higher concentration of metals than the incoming acid mine drainage, so as kind of a remediation in reverse. At that time, the lake was actually drained, and I had access to the sediments which actually accumulated on top of the organic matter. And in these pictures, you can see a couple of pictures showing the sediments which accumulated over 6 year periods. I was fortunate to have access to all these sediments. I was able to collect cores and at multiple locations and analyze them, as I mentioned, at the synchrotron, but also performing additional analysis. First, let's look at a couple of results that I obtained in a study which was published in 2017. So we start with the weathering coal mining materials, which is shown in here with black. During the weathering, the pyrite is the most important mineral, which weathers very fast with the production of ferrous iron and sulfate. This iron travel in solution, but in addition to that, there is a lot of colloidal and nanoparticles which also travel within the acid mine drainage. These colloidal particles are shown in here, are mostly silicate, which do not have, they weather very slowly. All these particulates and dissolved iron, they reach the lake on top of the bioreactor, the IMD lake. And in this lake, due to the biological processes, some of this incoming ferrous iron is oxidized to ferrous iron. During this process, the ferrous iron actually forms precipitates, which coat the detrital materials, the incoming silicates, and everything deposits as sediments at the bottom of the lake. So you can see in this picture the shormanite, which is iron oxyhydroxide with some sulfate in the structure, accumulates at the top. In time, the sulfate is being released, and what is left is the iron oxyhydroxide mineral called goethite. However, because at the bottom of these sediments the conditions are anoxic, iron is ferrous iron, ferric iron is reduced to ferrous iron, and this ferrous iron actually goes back in solution. What is left this white layer of sediments which contain a lot of silicate minerals. And the question that I was trying to answer with my synchrotron techniques is what happens with the contaminants such as arsenic during this cycling of iron within the acid mine drainage sediments. Since we were interested in arsenic, we analyzed the couple of cores for their chemical attributes. We are interested in iron because there were lots of iron minerals present, and also aluminum because most of the detrital material was aluminum rich, meaning clay minerals. So these were two cores, one which had a lot of iron minerals and one which had less iron minerals and lots of clay minerals, as is shown in here. And what we noticed is that the more clay minerals were present within the sediments, the higher the concentration of arsenic. So we hypothesized that actually the clay minerals were the one who were sequestering arsenic. We also analyzed the clay minerals, and you can see here that we identified kaolinite, illite, and some smectite. During weathering and interaction with acid mine drainage, these clay minerals became nanoparticles. You can see them in a couple of these pictures, offering a high surface area for reactivity. To really find out where arsenic was present within the sediments, we went to Argonne National Laboratory and I collected X-ray fluorescence data, XRF maps, XRD, and absorption data or ZAMES. And in a couple of slides, I will show some results. If you are interested, these results have been published. The publication is available on the internet. So what you see here, there are a couple of maps for different types of elements. This is an arsenic map on top, and you have additional ones for iron, gallium. What we found out is that arsenic actually was concentrated in a couple of hot spots, which you can see them here. We collected XRD data to find out what type of minerals or phases this arsenic was present in. A very important discovery that we made was that the clay minerals within the acid mine drainage sediments were the ones who were the main sequester of arsenic. So you can see here a couple of maps for iron, gallium, and arsenic, and this is a SEM picture with the weathered clay mineral. So arsenic was actually associated with these clay minerals, and we assume that actually there were precipitates forming on the clay surface which incorporated arsenic into their structure. So the presence of clay was very important in uptaking the arsenic from the acid mine drainage into the sediments. Moreover, the more clay minerals present in the sediments, like the white band that I showed you previously, the higher the content of arsenic being uptaken within the sediments. So this is a map, three-color map for iron, arsenic, and potassium, a proxy for the clay. And on this map, the highest concentration of arsenic actually is associated with the presence of clays. Also, when we looked at correlations between arsenic, for example, and gallium was used as a proxy for the clay, you can see that there are very clear correlations among these two chemical elements. One important conclusion of our study was that arsenic was immobilized by the detrital clay minerals. This immobilization consists in absorbed arsenic, incorporated probably in some precipitates, and also co-precipitating with other phases. The presence of clay, which was higher at the bottom of the IMD sediments, was again the place where most of the arsenic was sequestered. At the top of the sediments, which were mostly rich in iron type minerals, the concentration of arsenic was very, very low. Our conclusion could not be reached without the synchrotron work, which allows us to map in high detail the sediments, recognize the presence of different type of minerals, and also find out how arsenic was actually sequestered within the sediments. This was a very important conclusion because if you read many publications, they will advocate that actually the iron-rich precipitates are the one who sequester a lot of metals. But as we found out, were not actually the iron precipitates, but the clay within these iron-rich precipitates. I would like to acknowledge the funding agency, and this is Office of Surface Mining Reclamation and Enforcement. The Argonne National Laboratory is being funded by DOE and NSF. If you have any questions regarding my topic or my presentation, please do not hesitate to contact me. To conclude, thank you again for your invitation, and I hope everybody has a very wonderful meeting.